మీ మాట వినిపిస్తుంది నాకు.
సార్ నమస్తే సార్.
నమస్కారం, బాగున్నారా?
బాగున్నాను సార్, చాలా సంతోషం సార్. మీ వాల్యుబుల్ లెక్చర్ కోసం అందరం వెయిట్ చేస్తున్నాం.
అయ్యో ఏముందండి వాల్యుబుల్ లెక్చర్ అన్ని మామూలు.
సార్, విత్ యువర్ కైండ్ పర్మిషన్ వి స్టార్ట్ ద ప్రోగ్రామ్ సార్.
యా షూర్ అండి.
సారీ సార్, ప్లీజ్ సార్.
Okay, sir.
Yeah, go ahead.
So, good evening to all participants. On the occasion of 138th birth anniversary celebrations of Sri Srinivasa Ramanujan, our department is conducting a one-week online international workshop, Mathematics, Bridging Ideas and Innovations, MBII 2025, from 15th to 20th December 2025. On the first day, Dr. K. Lavanya Madam, Assistant Professor, Department of Computer Science, Acharya Nagarjuna University, Guntur, delivered a talk on a mathematical key for understanding quantum computing in AI era. On the second day, that is 16th December 2025, Dr. L. Jagannathan Sir, Professor, School of Computer Science and Engineering, Velir Institute of Technology, Chennai, delivered a talk on Mathematics of Transformers. More than 500 participants attended yesterday's session. Thank you one and all for your valuable participation in yesterday's session. I request our beloved head of the department, Dr. Kevilan Acharya Garu, to address the gathering for today's session. Sir, please.
Good evening to all. Respected eminent resource person, Dr. M.A. Srinivasa Garu, my esteemed faculty members and my dear students. On behalf of Department of Mathematics, I humbly welcome all of you to this third day of International Online Workshop. As head of the Department of Mathematics, convener of this international workshop, I am deeply honored to have this opportunity to speak a few words in today's section of International Workshop, which is being conducting in view of 138th birth anniversary celebrations of Sri Srinivasa Ramanujan, who is applauded as one of the greatest mathematicians in the world. This workshop is being planned so that students can improve their computational abilities in their engineering fields. The primary objective of conducting this international workshop is to focus on enhancing the computational skills in students' community in various fields of engineering. BTech students can build strong computational skills necessary for future success in their chosen disciplines by integrating academic knowledge with practical applications by dealing with real-world challenges. In this connection, all BTech students are advised to improve their computing skills. Our esteemed resource persons can provide insights in which computational skills are utilized in real-life situations, encouraging and motivating our students to enhance their inherent abilities in computing. So, with your worthwhile participation and collaborative cooperation, this program will be a fruitful one, undoubtedly. Today, we have a wonderful resource person with us. The resource person for today's section is Dr. M.A. Srinivasa Garu, retired professor, Department of Mathematics, JNTU College of Engineering, Science and Technology, Hyderabad. Dr. M.A. Srinivasa sir is not only an inspiring teacher, but also a source of motivation, guidance, and unconditional support to the student community. All through his career, Dr. M.A. Srinivasa Garu inspired thousands of students and also faculty members and won fame as best teacher. Since all of these, I can say that he is the best role model to all of us. On behalf of Department of Mathematics, I express my sincere thanks to Dr. M.A. Srinivasa sir for graciously accepting our request to deliver his valuable lecture in our international workshop. Thank you very much, sir. Finally, I strongly believe that all our participants can definitely utilize this opportunity to improve their computing skills in mathematics. All the best. Thank you. Thank you, one and all.
Thank you, sir. Thank you very much for your valuable message. Today is the third day in our one-week online international workshop. Today's speaker is Dr. M.A. Srinivasa Garu, Professor Emeritus, Department of Mathematics, JNTU, Hyderabad. Now I request one of our staff organizers, Srimati Alfaz Fatima, to present profound profile of Dr. M.A. Srinivasa Garu.
Good evening all. welcome you all. It's my privilege to introduce today's resource person, Dr. M.A.S. Srinivas Garu. Dr. M.A.S. Srinivas Garu is a professor emeritus JNTU College of Engineering, Science and Technology, Hyderabad. His entitled Contribution to Certain Nonlinear Biomathematical Models. He was a postdoctoral fellow at International Center of Theoretical Physics. He supervised and completed 8 PhDs, and currently 3 students are working for their PhDs under his guidance. He published 50 research articles in various reputed national and international journals. His areas of research are mathematical modeling of biological systems, boundary value problems, and fluid dynamics. He has completed 4 research projects funded by UGC and TechIP. He published 4 textbooks in mathematics and statistics, and 2 more books are in pipeline. He adopted modern teaching methods for visualizing theoretical concepts and created animations on topics like Fourier series, applications of integrations, eigenvalues and eigenvectors, and basic concept of calculus, which enhance the teaching learning process. He delivered a lecture on multiple integrals, which was webcasted to affiliated colleges of JNTU Hyderabad, and also delivered another lecture on partial differentiation, which was telecasted by Doordarshan Yadagiri channel, and both of these are available in YouTube. He is a life member of various professional societies and a member of several academic committees. He organized several conferences, workshops, and faculty development programs. He received National Merit Scholarship during 1983 to 85. He rendered his services as Academic Senate member of Andhra University. He was nominated as a panel member for AP Max Forum formed by Rajiv Vidya Mission, Government of AP in 2010. Dr. M.S. Srinivas sir is appreciated by one and all with his best way of teaching for the last 3 decades. His contributions to the department and JNTU Hyderabad in various roles and are remarkable. His helping nature, inspiring character, advanced teaching methods with visual edits, research capabilities are additional qualities in him apart from his goodness and vast experience in the field of education. Thank you.
Thank you, Fatima Madam, for your nice introduction about Dr. M.A. Srinivas Garu. Now I hand over the session to Srinivas Garu. Sir, please, sir.
Yeah. Good afternoon to one and all. I take this opportunity to thank the organizers, the head of the department, and the faculty members of Bapatla College of Engineering for
Sir, please.
making. Yeah. Am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah. For making me a part of this program as a resource person. I'm very much thankful to them. My compliments to all the distinguished teachers and the students who are participating in this program. The organizers rightly or aptly coined the title of this program as Mathematics, Bridging Ideas and Innovations. It's really a very good title. I appreciate them for choosing this title. As we know, mathematics serves as a bridge between connecting the abstract ideas. In mathematics, generally people feel that the number theory, abstract algebra, topology are the abstract ideas. From this side to the practical innovations, nowadays we are very much having these things, cryptography, quantum computing, robotics, machine learning, etc. So from this mathematics to these advanced innovations, the mathematics is a bridge. And these abstract ideas often lead to some breakthroughs, as all of us know. The number theory, which was the which is a basic important tool for developing this cryptography, abstract algebra for quantum computing, topology and robotics, etc. For example, if you take differential equations, it makes a bridge between the biology and the physics, where in the area of biomechanics. In fact, from last few centuries, various branches of mathematics were developed and they were not applied to any practical problems for so many years since their invention. Now, almost all of them have tremendous applications in present day advanced technologies. For example, if you take that elliptic curves, that topic was developed in 1600s, whereas the graph theory was developed in 1700s. All of you know is a very famous problem. Königsberg's problem is there that was solved in 1700. Then the seeds for linear algebra were laid down in 1800. So since these pure mathematical abstract ideas were not at all applied until 300 plus years, 16 plus in 1900, we got some kind of applications about them. So today the cryptography, Google page ranking, deep learning, all these things rely on these ideas. So mathematics is a practical, essential foundation of modern technology. So what is the role of this strong bridge, the mathematics? What is the role it plays? What bridge between the abstract ideas to innovations? What is the role it plays? We all use smartphones and social media, like online banking and some streaming apps like YouTube, etc. Every day we do it. So every single one of these technologies runs on mathematics. Mathematics is not just a subject, but a foundational tool that enables innovation. The title of my lecture is The Role of Mathematics in Technology and Engineering. These engineering problems require precision. This mathematics provides that precision, and also it makes some proper structure and predictability. Mathematics provides precision, structure, and predictability. All the three it provides. This advanced technology depends on accurate models and computations. We need accurate computations and proper models for that, for this advanced technology. To have them, the mathematics provides the tools to model them, to analyze them, and to predict system behavior. If you design anything without the validation, it is definitely unsafe. So mathematics design without mathematical validation is definitely an unsafe one. Without mathematics, modern systems would definitely fail. If mathematics do not support, definitely they will fail. Generally, engineers will convert that physical systems into mathematical models. While doing so, assumptions they will do. These assumptions, what they do is they simplify the reality. Whatever reality is there, they simplify it. But their assumptions should also be validated. For doing all those things, this mathematics helps a lot. All technological systems, what we talk about, they use mathematical models. In mathematical models, we do get equations. These equations describe their physical behavior. And there is a logic, what we generally use, this logic defines that system decisions. For making the decisions, we use this logic. My presentation today explains how this mathematics supports this modern technology and future technologies also. My lecture will, flow of my lecture will be like this. First, technologies also there, like machine learning, deep learning, and data science, what you call quantum computing, etc. So many things are there. I would like to map in a general way how what topic will be used in what technology. And after that, I'll give a brief idea because the why I'm calling it as a brief idea is I think this lecture is for the students of first and second years because they don't have the much idea on this in depth of mathematics. Simultaneously, their technologies also. I would like to give a nutshell how this brief ideas only I would like to give you how to make use of this mathematical domains. I don't want to teach any mathematics in my lecture. So I assume that the people will know about the mathematical domains and how these mathematical domains in different technologies, how to make use of them. After that, what for these different technologies, okay, for using mathematics, we have developed technologies. For what purpose those technologies are meant for? That is another one. After that, some case studies I'll discuss, and the future of mathematics and technology. If time permits, I'll cover up all the six. If not, maybe I can skip that one or two, maybe at fourth one and a fifth one I can skip. Or otherwise, I'll deal those things also. That depends on the time. Okay. So how mathematics helps the emerging technologies? That is our first topic. Mathematics helps the emerging technologies as foundation, backbone, and as an architect. So mathematics is not simply, generally people say mathematics is an abstract subject. In fact, it is not an abstract. It is the invisible architect of the digital revolution. Nowadays, everything is digitalized. So behind that, the architect is mathematics. Mathematics is the backbone of all engineering and technology. In fact, it is the foundation of modern high-tech systems from classical engineering to intelligent systems like machine learning, data science, quantum computing, robotics, etc. It is, in fact, this mathematics is more reliable. It is an efficient tool for innovation and the advancement of the technology. In addition to this foundation for all engineering analysis, it enables modeling. In addition to that, the mathematics ensures safety, efficiency, and reliability also. Mathematical abstraction and modeling. For example, if you are watching, say, on YouTube, we generally we watch several videos. For example, we are watching videos, lectures on mathematics, some topics on mathematics on YouTube for continuously for a week or so. If you do the next day, what happens is automatically you will get a notification regarding the same kind of videos will appear on your screen. This probably every one of you will experience that. So what the mission has done is the mission has to recognize the patterns of so many crores of people here, not only 2 or 3 or 100 throughout the world. Crores of people are doing the same thing simultaneously. Everyone is not watching that mathematics videos only. Everybody will watch their own interest videos. And crores of videos types are there. Crores of people are there. So this is a very, very high dimensional problem. For dealing such type of problems, manually it is not possible. Definitely we need the machines. For making the machines to do those operations, these mathematical tools are required. So the advanced technologies operate in very high dimensional, and all those are nonlinear environments. What this mathematics does is it will reduce the reduction of dimensionality. Mathematical abstraction allows engineers to represent real world systems using vectors. If we have a real world problem, we'll represent it vectors or maybe functions or some probability distributions and operations, depends on the data what you have. it depends on that, they will convert into those. Modern advanced technologies are mathematical systems at their core. If you take any previously, what happens is if you take civil engineers, for construction of a building or a bridge, mathematics is required, no doubt, but very less mathematics is required for the operation of that building or bridge. After construction of the bridge, the mathematics is not required. But whereas in the modern advanced technologies, using mathematics, if you develop a data science or machine learning or whatever it is, that technology requires the mathematics continuously. So it is the core part. Modern advanced technologies are mathematical systems at their core. Unlike classical engineering, as I just now mentioned, where mathematics was often a supporting tool, machine learning models, data-driven systems, and quantum computers are not built first and then analyzed later. First, building that machine learning system or some program like that, and after that they analyzed. They are mathematically designed from the starting point. In each and every point, in each and every stage, mathematics is there in the modern technologies. Coming to my second part, mapping of different domains of mathematics to different technologies. This is my second part. So first of all, in mathematics, basically the core, these are the three core domains which we need for this modern technologies: linear algebra, the calculus, statistics, and probability. These are the main thing. These three mathematical fields are so interconnected. A technology or a domain alone cannot sufficient to support any modern technology, but the combination of these things are required. These three mathematical fields are so interconnected that understanding any modern technology, if you want to understand any modern technology or if you want to design any modern technology, that requires the understanding of these three domains in depth. In addition to this, the discrete mathematics, number theory, and differential equations, these are the some supporting domains. Of course, some other domains are also there. This is not a we might not discuss everything in detail, but what we have to understand here is this mathematical these different mathematical fields work together. As if they work together, it is very powerful. What are the advanced technology? Generally, so far we are talking about advanced technology. Throughout my lecture, wherever I use the word advanced technology, probably it may lead to any one of these. But of course, this list is not exhaustive. Some more other things are also there. So these are the advanced technologies what nowadays we are all using: artificial intelligence and machine learning, cryptography and security, data science and analytics, quantum computing, robotics. Not only that, the list is not exhaustive. Much more technologies are there, like deep learning, neural networks, etc. But more or less, the same mathematical domains are needed for all these technologies. This is just for having a rough idea. Look at this diagram. So mathematics in modern technologies, it may be an AI and ML, or it may be cryptography and security, or it may be data science and analytics, it may be quantum computing and engineering robotics. If you take AI and ML, it requires linear algebra, calculus and optimization, probability and statistics. Once you come to cryptography and security, it requires number theory, it requires abstract algebra, it requires discrete mathematics. Whereas if you deal with data science and analytics, it requires statistics and inference, linear algebra and graph theory. Whereas quantum computing requires linear algebra, complex analysis and group theory. Whereas this engineering and robotics, it requires differential equations, control theory, and linear algebra. So just for different technologies, what different mathematical domains they require. In reverse way, suppose if you take any technology, in the technology, linear algebra takes a major part. Around 95% of linear algebra is required. Whatever technology you take, it requires linear algebra. The next comes probability and statistics, calculus, and discrete mathematics, differential equations. This number theory may be in cryptography and in some other areas it is required. That's why it only confine only to one or two things. Whereas linear algebra is required in all the domains. That's why I mentioned there are three crucial things. One is linear algebra, probability and statistics, and calculus. I suggest the students to concentrate more on linear algebra, probability, statistics, and calculus, especially the computer science and allied branch students. Concentrate on them. You will have wonderful understanding of your engineering subjects if you concentrate on this. Don't neglect these topics. Okay. These branches of mathematics in, let us say, if you take linear algebra, where it works. Just I'm dealing with the mapping of these two. Data at scale in the sense very large data. Linear algebra will deal with very large data. Graphics in video games and all, we will use it. And artificial intelligence, neural networks, and 3D games. Similarly, calculus for optimization. In optimization, we have this control, gradient descent, and robotics. And the probability statistics will be used in ML. In machine learning, it will be used for finding the risk analysis and email spam detection. And if you get several mails, simply some mails will be sent to spam. Why they are sending to spam? On what basis they are sending to spam? For that, actually, the behind tool is probability and statistics. And similarly for finance. Number theory we use for cryptography. How do you use it? In cryptography, the number theory used as the security. As there are several algorithms are there, like RSA algorithm, RSA encryption, blockchain, and all. Similarly, graph theory, if you take it, it is useful in networks. In networks, we use algorithms. Google PageRank. Google PageRank in this, so many people will use different pages, web pages. What is the best page, and what page is how many people search for that page very highly. All those things that gives Google PageRank, routing, etc. If you are using Google Maps, and if you once you start, if you deviate from it, again it shows another route. So for doing all the things, this graph theory is required. The routing is Google differential equations. It uses for modeling of systems, like how the disease spread is given, and for finding all the things, differential equations are used. Topology and geometry, if you take, it will be used in advanced machine learning for finding if you have so much of data, it will analyze the data and using again simultaneously for analyzing data, again probability statistics is also required. Quantum computing, for all these things it is useful. So these branches do not work in isolation. These branches, in the sense, the mathematics branches alone is not sufficient. We need a combination of these branches. Like deep learning, if you take, it takes linear algebra, calculus, probability, and statistics all combined. If you take cryptography, it requires number theory, group theory, and probability. So exclusively one branch of mathematics is not sufficient to understand or to develop the technology. Coming to the third one, brief idea on use of mathematical critical domains. How do you use these things? So no technology depends, as I said just now, no technology depends on exclusively on one branch of mathematics. It depends on the problem of study, depends on the innovation. Combination of mathematical tools is required. So, for example, if you take linear algebra, now I'll discuss in few slides, coming few slides, in how this linear algebra is useful in several branches. So linear algebra, if you take, it provides the mathematical language for representing and manipulating data at scale. Data in the sense, it may be an image, or it may be a sound, maybe it may be a text, or anything may be there. So every image you can represent with a matrix. Every sound you will represent with matrix. Every text you represent with matrix. Every network structure you represent with matrix. Every digital image is a matrix. Every neural network is a matrix. So every machine algorithm involves matrix operations. So whenever you represent the data in matrices, definitely the theory related to matrices is required. The linear algebra deals with those things. Linear algebra is the backbone of this modern technology. Data is represented as vectors, models as matrices, so and transformations as linear operators. Once you have a matrix, as students also know, that will find eigenvalues and eigenvectors. If you find the eigenvalues, those eigenvalues will be used to determine the system stability. So I don't know, some of your students may know that if the the real part of the eigenvalue is negative, then it is stable, and all some theories are there. I'm not going to deal with all the theories. Simply I'm giving the ideas about those things. So eigenvalue is used to determine the system's stability, and if you have any algorithm, whether that algorithm is convergent or not, and if you have data, how much it is spread, variance of the data, and all those things can be evaluated. It is the most important mathematical domain for technology professionals. The main power of linear algebra is matrix operations are extremely efficient on modern hardware. So because of the development simultaneously on the hardware, so we are able to do the operations very effectively and very fast, very speedily we are able to perform these matrix operations. And there are certain specifically mentioned GPUs, that is graphics processing units, and they are designed to perform matrix computations at incredible speeds. When you train a neural network, I used that word train. This is neural networks is a branch of machine learning. In machine learning, we'll train the machine to think in a specific way based on the data. So we train a neural network to classify the images. Suppose there are several images. If you want to classify them, and you are training it in neural networks, then what you have to do is you are essentially performing millions of matrix computations, matrix manipulations. So if you Google PageRank, previously in previous slides, once it has come. To know Google's PageRank, there are very practical importance of eigenvector, eigenvalue concept is there in Google PageRank. Data compression, if you have used data for reducing the dimensionality reduction, and also to deal with the principal component analysis, very useful analysis it is, uses the concept of eigenvalues and eigenvectors. So principal component analysis gives you what data is not required, what data is very much required, and all those things. What is the critical data is there in it, and everything will be learned there. Just to give a idea with very little bit mathematics, I'd like to give you a small thing so that you can understand how this linear algebra is helpful in this. A simple example, just to have an idea how linear algebra can be used in image processing or video games and etc. There are several algorithms. Actually, that algorithm does it for very large number of pixels. First, let me give you the idea. Suppose assume that imagine that you have a square with corners at 0, 0, 1, 0 and 0, 1. So I'll try to draw. See, you have one square here. Assume that is a square because of I'm not able to draw this properly with this digital pen. And this is 1, 0, and this is 1, 1, and this is 1, 0, 1. Yeah. Okay, this is x-axis, this is y-axis. Now, if I apply a rotation matrix, this square will rotate. If I apply a scaling matrix, this is x-axis. Suppose if I rotate the x-axis and y-axis, say some angle theta, probably the students will already learned at their intermediate level itself. That's why I have taken this simple example to make them understand how it is. And we do multiplication of matrices and all those things they do. But what happens actually they don't understand. But that is what actually required. Apply a rotation of a matrix, then the square will rotate. Apply a scaling matrix, the square will stretch. In video games, this rotation, scaling, etc., all these things will happen millions of times. Suppose if some ball is thrown up, if you see this in a graphics, so many multiplication of matrices will be performed by the computer in a matter of a millisecond. For example, if you take this matrix, with what we call it as the rotation matrix, this matrix is the rotation matrix. So with some angle theta, if I multiply, for example, say theta, there is one point, say 1, 2 is one point is there. And if I multiply these two, I'm getting this new point. That means it is changed to this. Similarly, if you take a scaling factor, this is the scaling matrix. This Sx and Sy are the scalings along x-axis and along y-axis. Then, if, for example, if you take 2, 0, 0, 1 by 3, this 1, 2 has changed to this point. And the uniform scaling means both x-axis and along x-axis and also along y-axis, the stretch is same. If S is less than 1 by 2, it is compression. If that S is greater than 1, it is elongation. So the scaling is that. So this is once you have a rotation, AB is the point in general. This will be rotated to the point A dash B dash. Then what will be the new coordinates once this rotate an angle theta? Of course, this example I am giving for 2 dimensions, but the thing is, this will be done for a large number of pixels, but we do it for very large scale. In 3 dimensions also they will be done. This is unequal scaling. Suppose originally you have a square like this, that square is changed to this rectangle. Along x-axis it is elongated, along y-axis it is compressed. So you got another thing. So like this is what, if you multiply one vector with another matrix, you are getting another vector, and that vector is this. Similarly, if you multiply, this is equal scaling. So in graphs, what we do is, if you take any point, for example, if you take any point, it will be treated as a pixel. So images are the matrices of pixel values. What is the pixel value here? There will be in color mode, there will be 3 things called RGB triples. R stands for red, green, and blue. This triplet is a set of numerical values. R will have some numerical value, G will have some numerical value, B will have some numerical value. Those numerical values vary from 0 to 255. If it is 255, simply a white color. If it is 0, it is a black color. If you change this RGB values in between 0 and 255, different kinds of colors we will get. These are the RGB triplet is a set of numerical values representing the intensities of the red, green, and blue color channels at a single pixel location. This is actually the foundation for the color images, displaying the color images on the digital screens. By varying these numbers, we get very wide spectrum of colors. So video games store these 3D models as matrices of vertex positions. Each pixel filter is a small matrix converted with the image. So in this way, the video graphing and all these things, for all those things, the linear algebra plays a major role. Just to give a glimpse, just to give an idea, in fact, the example what I have mentioned is very, very elementary. These kind of things with higher dimension, with higher speed happens there. Now let us see how we will see how calculus concepts are used in different technologies. For example, in machine learning, we have a loss function. In machine learning, what we do is we ask the machine to do certain activity. So for doing so, it will do some kind of things and it will do certain kind of predictions. So for after making these predictions, we'll frame a function called loss function, and the loss function uh, is a measure how wrong our predictions are. If our loss function is 0, that means there is no wrong and 100% correct. So always what we do is we minimize that loss function. Our goal is to minimize this loss function by adjusting the model parameters. Again, different parameters will contribute to that loss. And again, our aim is to find out what parameters are responsible for the loss. That also is another thing. So to deal the problems of this type, calculus plays a major role. There is one thing called gradient search. Gradient descent algorithm is there. This is very iteratively update the parameters to move down the loss of those predictions. And there is another thing called back propagation. Back propagation is another algorithm. What generally computers do, they compute how much this parameter contributed to the final error. What parameter is contributed to the final error, that also will be done. For doing that back propagation, we use that chain rule. I think all of you know the chain rule. That chain rule is very efficient, very effective in essential for finding the back propagation. So without calculus, machine learning as we know it nowadays, what machine learning is, it would not be possible without this calculus. Every time a neural network learns using calculus. In neural networks, it's a part of machine learning. It learns. For learning, that calculus is required. If, as a nutshell, if you see, the calculus is the mathematics for change, and it's a measure for change and optimization of machine learning training. Optimization techniques like gradient descent and that gradient descent optimization algorithm that enables that machine learning to improve themselves, improve the loss function. The chain rule enables back propagation neural networks. Every neural network update uses calculus based optimizations. This is how calculus is used in the technologies. Now we'll go for probability and statistics, another very important. First place for linear algebra, second place for probability and statistics, third place is for calculus. Because nowadays the calculus, probability and statistics is very much essential. Reason being, huge data is being generated in the world. Very huge data is being produced in the world. Dealing this data and studying its patterns is very crucial. Every day we are searching the websites for purchasing the article, maybe Amazon, or we are so much of browsing, you are doing it on internet. And for so much of data is, if you make a search, that is one data point. So much of data, so many people are generating every day. Based on the data, we need to make the pattern, we need to study the patterns. Based on the patterns, we need to give the conclusions. So for that, this probability and statistics is very much needed. Wherever there is uncertainty, the theory of probability and its distributions are used to model them and to know the variability of the data. This probability and statistics allows us to make sense of uncertainty and variability in the data. How much variability if you find the mean for the data, a central point you will get. From that, how much variability is there. And also this probability and statistics is essential in understanding real world messy data sets. Like if you have so many data sets, unnecessary things will be there, some critical things are there, and so much of very high dimensionality and reduce the dimensionality. So many things are there. For doing all the things, this probability and statistics will analyze this data. For analyzing, we do certain things, and after doing certain things, what we have done is that we will test whether the test is correct or not, so much things are there. Those, if any second year students are there here in probability and statistics, they will do testing of hypothesis and all. These are also very much required here. Statistical testing is crucial in determining if the observed differences are real or random. This is used in risk management, and in the data, if any anomalies is there, to find out that anomalies is also, we use this probability. And how do we use this probability statistics is another part. Once you know probability statistics in detail, then those discussions can be done. Here in this lecture, I am confining only to what mathematical domain is used where and how it will be used. Understanding statistics is essential for data literacy in the modern world. The probability statistics is critical because real world data is messy and uncertain, as I already mentioned it. Every machine learning model must account for randomness. Yeah. So, and also we distribute the data, how the distribution is. Generally, people generally say if you have a large data, it follows normal distribution. But the internet traffic patterns, they follow another distribution. Generally in engineering, you will not come across this power law distribution. The power law distribution curve will be like this. And the power law distribution curve will be like this. And about this distribution also we need to know. Understanding distributions of the data helps us model reality accurately. In healthcare sector, if you want to find out, suppose you have some data, limited data only you have, based on that limited data, if you answer this question, do we recommend a particular treatment based on this limited data, this probability statistics comes into picture and it will answer that question. Suppose if you have a portfolio, we do, every one of us generally do this share business and all. In that portfolio, in the finance, what is the risk in that portfolio? If you want to answer that question, the probability and statistics is required. And the people are predicting that a particular share will grow in so and so year, after 6 months it will grow up, it will go down, and all these things, these decisions, what they are doing, for that it is probability statistics is the main tool. Statistical hypothesis testing. So you have observed certain pattern based on some data, whether that pattern is statistically significant or it is just a random variation. If you want to know it, the statistical testing hypothesis is required. Suppose a company has two processes, two versions of the process. Which version is better to implement if they want to judge? For that also this probability statistics is required. The importance of web page is an very okay. This I think this is one example I can give you now, just to have an idea how probability and statistics can be used in machine learning for finding the page ranking. What is that page ranking? Page ranking is a method for rating web pages objectively and mechanically effectively measuring the human interest and attention devoted to them. For example, I'm browsing the web. One page I opened, after that another page, after that another page, after that another page. So many pages I am doing. I searched for it, and after that I got some interested page. I have gone through that. Similarly, the people, every people will do it. If a particular page may be viewed by several people, what page is viewed by so many people? If you want to know it, we compare that page rank. That is what they called page rank. So there is a sufficient algorithm that is which compute the page rank for large number of pages. But just to give you a small idea, just in a smaller scale, we learned how the page rank search will be done, so that you will appreciate how the probability and the statistics is helpful in understanding this page ranking. Imagine that a random surfer on the web following links from one page to another page is there. This page rank of any page is roughly the probability that the random shuffler will be land on a particular page. So that the page rank I am giving in terms of the probability. Okay, probability. Since more links go to the important pages, so everybody, if you see a particular page, that will have the more probability naturally. The surfer is more likely to end up there. So the behavior of the random surfer is an example of a Markov process. Markov process, probably some of you, those who second year students, if they learn, if you study this probability statistics paper, there they will get the Markov process. It is in fact a random process which do not depends only on the current state but not on the previous history. Suppose I have it at this particular page, I have chances of moving to several pages. With the different probabilities, I have to move from one page to the another page. That is what Markov process is there. Let us say for making you to understand in a better way, let us assume that we have only 5 pages. A, B, let us call them as A, B, C, D, E, with a set of 5 pages. Now, I am moving from one page to the other page. Page A, from page A to C, I am moving. Page A to B is also there is a chance of moving from A to B also there. From page A to C is also there. Similarly, from B to D, I will go. From B to C, I will go. Similarly, from C, D, and E, these are the different network what I have. Excuse me. Now, to start with, each page has the same rank. I can open any page. So because there are 5 pages are there, the probability of surfing a page is 1 by 5. That is 0.2. So this is again, if there are n pages, the initial rank, I call it as I mentioned now, rank is given in terms of the probability. So this is 0.2. Now, update this rank by adding up the weight of every page that links to it divided by the number of links emanating from the referring page. For example, if you have the page E, for page E from D to E you have, from C to E you have, okay, has 2 incoming links. One is C and another is D. So the page C contributes 1/3 of its current page rank to page E, because E is the only one of the 3 links from page C. From page C, if you say, it is going to D, from C it is going to E, and from C do you have again it is going to E. So from C there are 3 links. From C there are 3 links. Therefore, the chance of going to A or D or E is 1 by 3. Similarly, if you take D is going to E and D is going to A. So from D, if you have in the state D, it moves to C or E. Only chances are there. There 1 by 2 is that. Therefore, so this is 1 by 3. This is already you have 0.2 is there for 0.2 by 3 and 0.2 by 2. Totally it is 0.7. Now the 0.7 is for the rank of that E. So similarly in repeatedly you do this. If you apply this redistribution to every page in the graph after set and repeat this, one more thing is one important point here. If you take E, this page E, from E there is no from page E you are moving to no page, has no outward links. So redistribute its rank. If it is 0.2 is there, redistribute it to the remaining all. So this 0.2 by the remaining 4. So 1 by 4 of E's page rank is distributed to pages A, B, C, D, E. So 0.2 by 4 is to be added to other things. This idea behind this model is that users will keep searching if they reach a dead end. So if they reach a dead end, still they will again there is a chance of going back to A, B, or C, or D. So apply this redistribution to every page in the graph. Repeat this process until the page rank stabilizes. So The page rank algorithm adds a damping factor. In fact, that is not, I am not including that here. The damping factor at each stage to model the fact that you just stop searching. So this is somehow an idea I am giving you how that page ranking will be done. Now we'll see how discrete mathematics and number theory concepts are used in different technologies. Discrete mathematics deals with the countable distinct objects as opposed to continuous mathematics. If it is not discrete, is not if it is not a continuous mathematics, we go for discrete. A graph theory, if you take that, graph theory study is a study of networks of connected nodes. This is crucial for social networks. The graph theory generally we use in social networks. Who is connected to whom? For example, if you take Facebook or Instagram, we do. So you will get some friend requests from several people who are the friends of your friends, because you are linked to your friend is linked to another person. Probably you may also know, based on that it will give a link. So who is connected whom, based on that, the social networks. Transportation of networks, so optimal route. For example, in Google Maps, it will give the correct, several routes are there from place A to place B, which is the optimal one. Sometimes if you observe, in Google Maps, probably there will be some settings whether you want to optimize the distance, whether you want to optimize the time. So there may be small traffic will be less, so that you can go fast, and in less time you can reach the destination, but the distance will be more. Whereas in another route, you may have, though you have very traffic is there, you may, even if you take longer time, the distance is less. So based on your requirement, it will give the optimal route. For doing all those things, simply if you tap that button that I want the Google map with less time, then corresponding route you will get. If you put the option that I want the shortest distance, then that route it will give. That for deciding all the things, this graph theory plays a major role. And we do a lot of purchasings and all, your interest and everything will be learned by the machine, and it will give the notifications, recommendations it will give, which product is best and all, in Amazon and Flipkart. For doing all the things, behind story is graph theory. If graph theory is not there, nowadays we don't get all these facilities. Combinatorics helps us count possibilities and understand algorithm complexities. As you know, algorithms, different algorithms will be there. The complexity of the algorithm means it is a measure the number of resources that algorithm utilizes. How much time it utilizes, time in the sense not our time, it is computer time for run that program. How much time it takes, and also how much memory it takes. Based on that, we decide the complexity. And that complexity will be in terms of the input. If you have n parameters, that will be given in terms of n. Suppose if I say the complexity of the algorithm is order n square, it means if you increase the number of inputs, or if you decrease the number of inputs, the corresponding complexity will decrease or increase based on that, and square of the type. Sometimes algorithms of n log n complexity, order n complexity, order 1 complexity. Order 1 complexity means it is constant, but even if you increase the number of inputs, it will not change. So like that, we decide the complexity of an algorithm, and which is very crucial, because we always try to optimize. Again, calculus comes into picture. We always optimize the time of utilization, my computer time, and also we optimize the memory. So for doing this optimization, sometimes if you sacrifice that, for memory, time will be less. Sometimes if you sacrifice time, the memory may be less. So like that combination of those things, based on that, we find the complexity of every algorithm. So for example, this bubble sort is of order n square. Number theory, as everyone, number theory is the study of integers and their properties, like factoring large numbers into primes. Like that, the number theory is some theory about the numbers. I think all of you know it. This theory provides the mathematical foundation for cryptography. Cryptography is basically a science of sending some communication with security. Cryptography basically means that sending a communication with security. How to secure it? For that, the number theory comes into picture. And while sending that communicating, whatever information is there at the one end, by reaching the other end, it should not have any loss. Complete information it has to pass on. And for doing so, this mathematical technique, it's a this crypto protecting information using mathematical techniques to ensure confidentiality. Nobody should know it, integrity, and authentication. That's what actually the cryptography means. It transforms the readable data. Suppose all of you know it. If you press the amount, say the 1 lakh rupees in your mobile from say Phone Pay or Google Pay, and the machine should not know that by the time it reaches the other end, it should not be revealed to other person that it is 1 lakh. So again, it is to be encrypted and decrypted, and it will go. It transforms readable data into unreadable form, preventing unauthorized access and tampering. There are several advanced algorithms like RSA algorithm for encryption and decryption. So for all these things, that number theory plays an important role. Computers fundamentally work with discrete values like bits, integers, and logical operations. Understanding this discrete mathematics is very much essential for understanding the computational procedures. If you want to understand the computational procedure, all this discrete mathematics is required. Now coming to this differential equation, basically differential equations are used to model the real world problems, and the solutions of these equations will help us to design the systems. Differential equations doesn't play much role in the development of the technologies. Differential equations describe how quantities change over time and space. They are fundamental to physics, chemistry, biology, and engineering. Few of the applications are if you have weather forecasting. That weather forecasting relies on solving atmospheric differential equations. Similarly, aircraft design, if you want to do it, it is based on the aerodynamic differential equations to optimize the wing shapes. Similarly, epidemic modeling, that again a differential equations to predict how the disease is spread. For answering these kind of questions, these differential equations are used. The differential equations are mainly, as I said, they are mainly used to model the real world problems. Once you make a model, mathematical model, you will have several equations and will solve it. The solutions of these equations will help us to design the systems. And recently, one fascinating development is that differential equations are solved using neural networks. The neural networks is another, as I said, machine learning. The machine has learned how to solve a differential equation that using this neural networks algorithm. So nowadays, the differential equations are solved. Because of this neural network, solving those differential equations has become very, very fast. Google's DeepMind's neural network solver can find solutions to very complex partial differential equation faster than the traditional numerical methods. Those who are doing PhDs, they do use this DeepMind's neural network solver for solving the partial differential equations. Once you defeat that PDE, it will give the solution. Again, the backbone for that is the numerical methods is the backbone. This represents a beautiful synthesis of pure mathematics, that is differential equations, and modern artificial neural networks. So this is apt for the present today's program. A pure mathematics one, that is differential equations, is converted to modern using modern AI to neural networks for solving the differential equations, creating entirely new possibilities for scientific computation. For that, the differential equation are used. Instead of solving partial differential equations analytically or through traditional numerical methods, we can now learn the solution with the neural networks. And coming to the fourth topic, another three topics are there. Fourth topic, what the technologies are meant for. I have already given a list of technologies. These technologies are meant for what purpose? So far, what we have seen is how different domains of mathematics are used in different technologies. How linear algebra used in different technologies. How the probability statistics is used in different technologies. How other domains are used in different technologies. Now, I would like to briefly explain what actually these technologies are meant for. Okay, we have developed the technology, say machine learning, maybe data science or something like that. Why, for what purpose we have meant for it? For what purpose they are used? The quantum computing, and for what purpose we use that? So let us see a few of the things. Maybe say, for example, take the data science. We all of us are talking about data science nowadays. What is this? Where this data science is applicable? For what purpose do we use this data science? Data science is applied. It's in fact is an applied statistics combined with the machine learning and engineering. So data science is the applied statistics plus machine learning. That is what data science is. Modern business generate enormous data, as I already we discussed. It generates so much of data, like customers' transactions. So many transactions we do on several websites, maybe on Amazon, maybe on Google, maybe on some other thing, maybe on we'll browse and Facebook, Meta. Now it calling it Meta, and so many things. On so many platforms we do so many transactions, and read so many sensor readings. We interact with so many people, whatnot. We every morning, once we have time of 10 minutes, we open our mobile and lot of things. So much of, once you open a phone and if you browse, it generates one data. That you can imagine how much data nowadays it is being generated. So it extracts meaningful patterns from noise at scale. If the system, it definitely understands my patterns. What messages generally, what videos I am looking at, what news I am reading, and all these things based on my things, it will make certain patterns. It extracts meaningful patterns from noise at scale. So large from data it extracts. For example, predicting customer behavior, and will they buy this particular item, will they buy that particular item, and all those things, they'll do it. Assessing financial risk. And one more thing, probably every one of you might have observed, wherever we go several hotels, and automatically a message will come to you, give the rating for it and all. So how the Google is observing us by using that location, and that is using no person will be there, and the machine will understand where you have gone and what you have eaten. Every time if you are going for a non-vegetarian restaurant, it will give the feedback, it will give the notification about that kind of restaurants. If you go for vegetarian restaurants, it will give the notifications for that. Assessing financial risk. What's the portfolio's risk? Risks stratification for the parents, and inventory, pricing, staffing, and for all the data, this kind of patterns it will make. Data science begins with statistics. Before building complex models, you must understand your data. How do you understand data? We find the mean. So what is the average value? We find the median, almost a middle value, and how much spread is there from the mean as well as from the median, and it will reveal the several patterns, like what are the trends and what are the outliers, what are the correlations. patterns in the sense seasonal trends, correlation between the two variables, and it will give several kinds of observations it will do. Is one version of a website is better than the other? Does a medical treatment work? Is this pattern real or random? For answering these kind of questions, the data is a testing of hypothesis. Now, this quantum computing is another thing nowadays everybody is talking about, especially in Andhra Pradesh. The Chief Minister is also talking about quantum computing. Lot more things are there. So, what is a quantum computing? Represents the computational mathematics. It's where abstract mathematics meets quantum mechanics for revolutionary computing. Quantum computing quantum computing's mathematical foundation is linear algebra and complex numbers. The complex numbers and the linear algebra is very much needed for the quantum computing. Generally, in computers, we generally use bits, 0 or 1. But in quantum computers, we use qubits. Qubit means quantum bit. Qubit means quantum bit. What is that quantum bit? Quantum bit is said there are two-dimensional vectors in complex Hilbert spaces. Qubits are two-dimensional vectors in complex Hilbert spaces. These are the fundamental units of information in quantum computing. For example, in ordinary computers, either one is on and off is 0. So every information to the computer will be given in terms of zeros and ones only. Whereas in quantum computers, we give the information in terms of 0, 1, or a combination of both. Okay. There is in mathematics, there is one thing called Bloch sphere. So you can imagine a sphere, on the surface of the sphere, there will be so many qubits. For example, I am calling this 1, 0 as this symbol 0 and this 1 as 0, 1. Now, qubit can be a linear combination of this alpha times of this 0, beta times of that. A qubit may be visualized as a unit vector in the plane. So it is 0, it is 1. A linear, any time if you take a point, it's a linear combination of this x and y. If you take any, what do you call, if you take a unit circle, if you take a unit circle on this. At this point, you will have alpha times of this, beta times of this. This is 0 and this is 1. And this will be alpha times of this and beta times. This is a vector, 0 vector. Alpha times of that unit vector will be this. This is the unit vector 1, this one. And this vector is beta times of this plus this will be given to this. Therefore, this is, in general, the alpha and beta are the complex numbers. So the quantum computers, what the advantage of quantum computers instead of picking 0 and 1, if you use their combination, if you use the qubits, quantum computers can explore exponentially many computational paths simultaneously. The speed will be tremendous and enormous. You can perform operations affecting all superposition terms simultaneously. This is where quantum speed comes from, exploring exponentially many states in parallel. Yeah. As I mentioned, qubit leverage quantum mechanics to exist as 0, 1 or a superposition of both. The harness phenomena like superposition and entanglement to solve problems intractable for even the most powerful supercomputers with real-world uses. The uses in the drug discovery, finance, cyber security at several places. The computational, once the computational speed is enormous, we can do we can answer so many questions. This enables solving certain problems exponentially faster. The mathematical foundations required for our Hilbert spaces for quantum computing, if you want to have a good knowledge of that, you need to know what Hilbert spaces, unitary transformations, tensor products. These are the things what you need for this quantum computing. That is, Hilbert spaces means it infinite dimensional vector spaces. Unitary transformation is a reversible operation. This unitary transformation is a reversible transformation, combining quantum systems. And in quantum computing, these are the several algorithms which makes this machine to compute very fastly. Some of them are Shor's algorithm, Grover's algorithm, optimization. Quantum computers are not faster at everything. So there are some, they excel at specific, only it works only for certain kind of problems, not for all the kinds of things. Machine learning. Machine learning is a broad concept where algorithms learn from data to perform tasks without explicit program. For doing a task, no need of writing a separate program from it. It automatically understands. So machine learning is a broad concept where algorithms learn from data, whatever data you have from that data, there are certain algorithms. Those algorithms will learn to perform the task. The neural networks, as I said previously, it is a subset of this machine learning. It is a specific type of machine learning algorithm. The neural networks is a specific type of machine learning algorithm. Using interconnected nodes, those nodes we call it as them as neurons in layers to process information. Machine learning goal is to enabling computers to learn from data. Machine learning, what it does is its goal is to understand the data from the computers. Neural networks uses layers of neurons to automatically learn features and complex relationships for unstructured data. Machine learning is a way to train software called a model to make predictions or generate content using data. So these are the several purposes where this machine learning is used. So supervised learning uses labeled data to make predictions. So this machine learning will do some kind of predictions. So unsupervised learning identifies patterns. Unsupervised in the sense they are texts and all. These are those kind of data we call it as unsupervised. Machine learning helps in generative AI, creates new content such as text, images, or music. For this also, some learning patterns are required. So these are several functionalities are there in machine learning. I'd like to simply skip them. So some case studies, let us see. The first case study is, for example, we all of us see Netflix. We get Netflix recommendations. If we watch movies of certain movies, based on that, do you like this movie? Do you like that movie? And all these things you will get. What's the background going on it? This Netflix has approximately so many subscribers, say for example 250 million subscribers, and say several titles they will see in every day. Personalizing recommendations at this scale requires sophisticated mathematics. So if you want to give my personal recommendation is required, they need to so much of data is available. Out of it, they have to give me my recommendation. They need algorithm that learn from the behavior. So the Netflix uses this matrix factorization. This algorithm, this Netflix uses. Imagine a matrix where there are rows, some huge matrix you imagine. In each row, there are users. In each column, there are movies. And rows are related to rows. Rows are for users. Columns are for movies. Movies is some entity. And in matrix will enter them. That entering is ratings or engagement, whether a particular user A is using a movie M1. A M1 in that place. If they see that movie, they will put 1 or otherwise 0. Like that. So you enormous number of 250 million subscribers and 10,000 titles. That means 250 million by 10,000. Such huge matrix is available there. So this matrix is a sparse matrix. What I think many of you know the sparse matrix means. Sparse matrix means a matrix in which the entries, most of the entries are zeros. Most users, here zero means most of the users have not watched some particular type of movie. Everybody don't watch every movie. We use only Telugu movies, whereas other people will use only Tamil movies and like that. And some of us will watch the Hindi and also English movies. So no need of it's not compulsory that everyone has to watch every movie. So definitely there will be zeros in as the entries. So that's what is called a sparse matrix. Now, huge matrix. So what this matrix factorization does is it reduces the high dimensional sparse data to a low dimensional dense representation. So it reduces the dimensionality. Instead of sorting billions of sparse ratings, you store hundreds of millions. Instead of storing billions of zeros there, we store only few hundreds of millions of dense vectors. The algorithm, what it does, it decomposes the large sparse matrix what you have into smaller dense matrices. It will reduce this to two matrices. One matrix will represent the latent features of the users. Other one represent the latent features of the movies. So users and movers are represented now as vectors. Similarly, between vector spread rating probabilities also it will be given. So how many if I how many people are using a particular, what is the probability of watching a particular movie by a particular person and all those things. So Netflix uses techniques like singular value decomposition. Probably this is even in the syllabus of engineering mathematics also in many universities are including singular value decomposition. It's a fundamental linear algebra operation which reduces the dimensionality, and it's very important one for the engineering students. The modern Netflix uses neural network approaches like neural collaborative filtering. This is for to predict ratings by understanding latent patterns in user performances. The second example, if you take, it is Meta's feed ranking algorithm. So Meta, all of you know that Facebook and this Instagram, this Meta company has taken up. So Meta's feed ranking algorithm determines what appears at the top of your Facebook or Instagram feed. That is what Meta's feed rank. For my Facebook, my ranking is different. Now, some kind of pages I'll like more. Your ranking may be different. This is one of the most complex mathematical systems in the world. So it's a very, very big scale problem. Billions of users, millions of new posts every minute, trillions of ranking decisions daily. Selection is very, very critical. Such a huge problem it is. So for treating such for dealing with such kind of problems, the Meta uses machine learning models like it extracts features from posts and users. Features from post like, is it from a close friend? Whatever post I get, is that post is from a close friend to whom I generally communicate? Or how many likes are there? What is the content of the category? Like this, these are the features from different posts. Features from users. What you have engaged with before. Is that user previously used, or who do you interact with most, with whom you are interacting more, and that's a kind of features generally it will observe. These become feature vectors combined in deep learning models. This kind of feature, every feature, they will take it as a vector and they will form a vector space, and all so much of theory is there based on that. And they will develop one model called deep learning. From those, they will do those predictions. This predict engagement is using for prediction. They will use the neural networks. Again, as I said, a gradient descent method they will use for from a technique from the calculus. All this computation happens in real time for billions of users. The more effective computational techniques are required for doing that. So my last topic of my lecture is the future of mathematics and technology. What is the future of mathematics? What is the future technology? Now, the future technology is this: the integration of artificial intelligence and this quantum. Combining these two is the future. Quantum machine learning use quantum computers to train machine learning models faster. And another quantum support vector machine. This potential exponential speed up. This is this the challenge here is translating classical algorithms to quantum algorithms is the challenge. While doing those translations, we need to maintain the advantage of the quantum. So if we do it, this is the future technology, what generally we expect, so that much more faster things will get. And what is the future mathematics? In mathematics, there are several conjectures are there. As you know, conjecture means a mathematical statement which we believe that it is true, but not yet proven. We don't prove it, but clearly it says that yes, it is true. That we can clearly understand, but proof is not there. Like that, there are several conjectures, and they are called open problems also. If somebody makes them prove, probably from that mathematical from that mathematical concepts, a new technologies may evolve. So future mathematics is in solving these kind of open problems. For example, if you take in mathematics, there is one conjecture called Riemann hypothesis conjecture. There is one function that's what called Riemann zeta function. If you want to know what is Riemann zeta function, go through the several books on number theory. You will understand what actually the Riemann zeta function is. If you have a function, definitely, for example, if you take x square minus 5x plus 6 is equal to 0, if 5x plus 6 is the function, for some values of x, it will become 0. If I want to find for what values of x, it becomes 0. That means if I call that Riemann zeta function as zx, for example, say, zx will become 0 for only negative even integers. And that equation zx is equal to 0 has real and complex roots also. Always even negative integers, minus 2, minus 4, etc. And it has complex root is also there, but real part of that complex root is 1 by 2. So the root for the zeta function is always 1 by 2 plus 1 by 2 is always fixed. So if you see that zeta function, if you substitute there, definitely it will satisfy. But getting a proof for it is very difficult. That is still an open problem. Any student is interested to solve these things, go number will be 4 because it's again by 2. The 4 again by 2, that is 2. 2 by 2, that is 1. Suppose if I start with say 11, because it is an odd number, multiply it with 3 and plus 1. And go on doing it. It will, if I take 11, what is the next number? 11 into 3, 33. 33 plus 1, that is 44. 44, that 3 and means 3 into 11, 33. 33 plus 1, sorry, 34. 34 by, because it is 2, even number, divided by 2, 17. Again, 17 multiply by 2 and add 1 like this. If you go, I'll give a simple example so that we'll finish early. Suppose if you take 5 and do multiply it with 3, 3n plus 3, 15 plus 1, 16. 16 by 2, that is 8. 8 by 2, 4. 4 by 2, 2. 2 by 2, 1. So like this, it will always end up with 1. This is the conjecture. So for knowing it is very easy, but the proof is not so far learned. If you crack this one, definitely this will become a very, very interesting problem, and it may be used in some technology to do it very good thing. Similarly, there is another problem, tin prime conjecture. So two prime numbers are called twin primes if their difference is 2. 3 and 5 are prime numbers, that is difference is 2. 5, 7, 11, 13, 17, 19, 29, 31, like this. We'll get different names, different kinds of prime numbers whose difference is 2. After this also you will get. But the conjecture says that there are infinitely many pairs of twin primes. So I
Yes,
have
sir.
shown them so many tremendous applications of those mathematics, whatever they learned in their engineering course like linear algebra, matrix and eigenvalues, eigenvectors, and also
sir.
several things. Whatever
Yes,
they
sir.
are learning in their engineering mathematics, they're all useful, especially because everyone nowadays they have to learn these computer courses, no? So they,
Yes,
without
sir.
computers, nothing is there. Everybody will come across either ML or everything. They are, even after they join the software job, they need to do all the things. And
Yes,
even
sir.
if they go for research programs also, these are very much required. So
Sir.
because they don't know about, for example, if you take a first year mathematics students, they don't know what probability and statistics, what is testing hypothesis. Therefore, I cannot teach them the probability and statistics, but what I can give them is where this probability statistics is useful. So once they learn probability statistics, they will show some kind of interest in learning the things because they know that this has applications in their computer science courses.
Yes, sir.
So
Really
keeping that in mind only, I have taken this. Previous in last year and before last year, I have given different talk
Yes,
on
sir.
modeling and all, and learning how to learn mathematics and all. But
Sir,
this time,
really it is useful to our students, sir.
because this is my consecutive third year of giving a lecture, so every time if I give the same kind of things, probably
Yes,
it will
sir.
not be good. That's why I changed this.
Yes, sir. Really it is wonderful lecture, sir. Definitely our students will be benefited. So thank you one and all for your good response and valuable support. Expecting the same cooperation for the remaining sections also. So today's section concludes with the vote of thanks by myself. Good evening to all. On behalf of Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource person, Dr. M.A. Srinivas Garu, Professor Emeritus, retired Professor, Department of Mathematics, JNTU Hyderabad, who gave such a good and informative presentation on role of mathematics in technology. Despite of his busy work schedule, he gladly accepted our invitation and gave a valuable talk in today's section. Thank you very much, sir. I would like to thank our principal madam and our magnanimous management, Bapatla Education Society, for providing us all the facilities and encouraging us to conduct this program. Without their support, it would not be possible to conduct such a program today systematically. I would also like to thank Dr. K. Manideep Garu, HOD, Department of AML, Sri N. Kirankumar Garu, MC HOD, Sri Koteswarao Garu, Faculty of MCA Department, and Sri U. Venugopal Garu, who are sincerely extending their technical support to us in conducting this international workshop. Thank you one and all. Sir, thank you once again. I am very much thankful to you, sir, for your valuable and wonderful lecture.
Thank you.
Thank you, sir.
If it is helpful for the students, I will be more happy.
Thank you, sir.
Thank you very much.
Srinivas garu, thank you very much, Andy.
Thank you.
Sir,
Meanwhile, there is a small interruption for me.
Yeah, no problem.
Your responsibility, sir, with your kind permission. Sorry, sir.
Sir, thank you, sir. Thank you very much, sir, for your wonderful lecture.
Yeah, thank you.
Sorry,
I
sir,
hope-
because of sorry, sir, because of having unexpected problem, I took your responsibility. Kindly
Thank you, sir.
pardon me, sir.
Thank you, sir. Thank you.
Okay.
Thank you, sir. Thank you.
Yes, I'm
Sir,
leaving. I'm
kindly
leaving
extend
now.
Sir, in the same way, kindly extend your kind cooperation to us, sir, in future also.
Sure, definitely.
Thank you, Srinivas garu.
Whatever I can do, I do. Definitely do it.
Thank
No
you,
problem
sir.
at all.
Thank you.
So
Thank
one request to participants. All of you, please fill the feedback link, which I am going to share shortly in your WhatsApp group. Don't forget to fill the feedback. Immediately fill the feedback. Also, you please attend all the sessions to the possible extent. Okay. Thank you very much. Sir, you can leave, sir. Thank you, sir.
Thank you very much.
So,
Namaste
Srinivas
to
garu,
everyone.
thank you very much, sir.
so kindly bless us in the same way, sir.
Sir, I am closing the session, sir. Thank you, sir.
Okay, sir. Okay, no
Okay.
problem, sir.
End meeting, Kotal.